Okay, anyway, let's continue for this exercise. And so most probably we're going to finish up all this exercise. And I'll give you homework, number 3. Okay, let's look at question number 9. So basically what we are doing is we try to apply this activity concept, okay, and to solve actually some equilibrium calculation or to know whether actually the direction is to forward or backward, okay. So that's what we are doing. So question number 9. So this is the recovery of the zinc by using the vacuum distillation. Zinc. For me, it's very difficult to pronunciate the Z and the G. My wife always says that you don't pronunciate Z properly. And it's very difficult. Anyway, when I actually went to the Montreal first time as a professor, that was 2007, and I worked in the McGill University for 10 years. So the first year, so I arrived in the Montreal almost end of the August in 2007, and they start asking me to give the lecture from the beginning of September. And then my second actually, so that was the first term, and then the next term I gave another lecture, which is about the extractive metallurgy, so extraction of the metals from the ores. And end of that actually the lecture, the student give the evaluation report, and they say, okay, professor looks like know a lot, but he don't speak English properly, especially zinc. There's no zinc, zinc, and yeah. Anyway, so I always try to make sure I pronunciate the Z correctly, but still it's very difficult. Anyway, so in order to remove the Z10 from the lead, okay, PB. So we suggest the vacuum distillation process at 500 degrees Celsius and calculate the necessary vacuum in total to reduce the amount of the Z10 down to the 0.01 atomic percent, okay? And we have the Hellman active coefficient, and also we have the PZ10 naught. So log 10 PZ10 naught. That actually PZ10 naught is the vapor pressure of the pure zinc. So when you have pure the Z10 in the liquid state, it will have the vaporization, so it will make actually gas, and that actually so P naught means when it is pure, okay. So we compare the actual activities P over P naught, yeah. So it's P naught. That's the P naught here, okay. So let's try to solve this one, number 9. So basically, so we have here PB and Z10, and we are making this P total to certain value. So it's less than 1 atm basically, okay. Then it will have evaporation of this Z10 as Z10 gas phase, okay. So, and temperature, Kelvin, and equal to 11, and log, so it's log, it's P, some value. So this is like 12 minus 60, 6670 over the T, minus 1.126 log T, and etc. In this unit is total. Okay. So basically this means, so when you have the pure Z10 liquid phase, so this is liquid phase, and this pressure PZ10 is PZ10 now. That's what it means. Okay? And so the amount, so when we actually, at least we know that, okay, so we want to make this one 0.01 atomic percent. That's what we want to obtain. Okay? So mole fraction, in terms of mole fraction, is 10 to the minus 4. Okay? So now let's try to actually make a chemical reaction. So, which chemical reaction we have to set up? I mean, it doesn't give any kind of chemical reaction. So you have to think about what chemical reaction you want to set up here. Yeah? So we want to know this pressure, total pressure, and partial pressure of Zn is mole fraction times total pressure. That's what we have to get. Okay? And that gas is equated with Zn in the liquid phase, in the lead, inside of lead. Okay? However, whether Zn is inside of lead, whether Zn is inside of the silver or gold, whatever it is, we still deal with Zn as Zn. Yeah? So standard is Zn. So we have to set up like this. Zn liquid become Zn gas phase. And this delta G naught we don't know from this question because it doesn't. We don't have this information in this from this one. Now, I mean this information, P not Zn, okay. This is pure Zn become pure gas phase, yeah? And this is basically pure become pure. So this information gives actually what is delta G naught. Okay, so for example, at the equilibrium state, so delta G should be 0. So let's take this case number, for example, 1 and case number. So for case number 1, case 1, so when this is in equilibrium, so we say delta G naught, so this delta G naught equal to minus RT ln activity. So we can set up in this way, yeah? And however, in this case, this one equal to 1 because it's pure Zn, okay? And this one is basically same as Zn, pure P naught of Zn because it's pure, the gas phase pressure here, and that's actually the given here. This one, this information can go inside here, yeah? Okay? So if we calculate what's the partial pressure or P naught of Zn at 500 degrees Celsius, 773 Kelvin. So we enter 773 Kelvin, we calculate what's the P naught Zn, but this is in torr. Theoretically, this value inside should be ATM. So you have to convert torr to the ATM. Okay? Is it okay? So, and then we can obtain this delta G naught at 773 Kelvin. Okay? So once we know this one, now we can apply this same thing for the case number 2 as well, yeah? So case number 2, so at equilibrium, delta G naught. So we are talking about same delta G naught equal to minus RT ln now P Zn and over activity of Zn. And this activity Zn is activity coefficient of Zn times mole fraction. The mole fraction we want to target is 10 to the minus 4. Yeah. So 10 to the minus 4. And this is 11. We know this value. Okay. So, and this value is same. So in the end, I think even without actually solving this one to get this one, you can in fact compare this value with this value. These two should be same, yeah? So this one should be same as this one. Am I right? The same delta G naught at same temperature. Okay? So we can set up in the end, in this case we can set up in this way. So P naught Zn, so equal to and this one is mole fraction of Zn in gas phase times P total. Yeah, partial pressure is the mole fraction of the gas phase plus times P total. And mole fraction, we can assume this is equal to 1. And there will be small amount of the lead gas phase, but I mean there's no specification, so it means probably lead evaporation is nearly 0. Okay, so you can assume that there's only actually the Zn gas phase. So this is 1 and P total. So basically P total is same as the partial pressure in this case. Okay, so you calculate this one, you can find what's the answer. Okay, in this case, what is nice is you don't have to now convert this one into the ATM because it's tall to tall, it's same unit. Yeah. Okay. So how many tall is one ATM? Huh? 760 tall is the one ATM, yeah? So one ATM is 760 millimilli Hg. Yeah, millimilli Hg. Millimilli Hg is same as the tall. Okay? Am I right? And one ATM is 10 to the 5 Pascal. Am I right? So pressure unit. So one ATM, theoretically it's slightly different, but you can almost say 99.9% same. One ATM, 1 bar is same basically. And this is 6 Pascal. So we call it 0.1 megapascal or 10 to the 5 Pascal. And then okay? So that's typical unit we are using for the pressure. So we keep, one of the actual points you have to really realize is, even when you are talking about solution, even you deal with the solution, when you set up the chemical reaction, you have to really set up what kind of reaction I'm really looking for in this actual question. You don't have to, when you set up the chemical reaction, you don't have to worry about whether this is part of solution or not, because reaction itself is independent of your environment. Okay? So chemical reaction is independent of chemical reaction. In general, the chemical reaction, the formula itself is independent of your condition, of the surrounding. Okay? But once you set up, when you do the equilibrium condition, now that is actually depending on your surrounding. Okay? So the very first thing is always you have to think about what chemical reaction I have to set up. Okay? So whenever you see the problem like this, you have to always think about, okay, there's no chemical reaction given. Now I have to think about myself, by yourself. And then you have to really think about, okay, what chemical reaction I have to set up. Once you know that, the rest of them is, very easy because most of the information is available around there already. Very good? Okay, let's look at question number 10. So now we have a mixture of liquid magnesium and the zinc and gas phase, and standard boiling temperature and enthalpy and entropy of liquid magnesium is given in this value, this table here. So the magnesium, the boiling temperature or vaporization temperature, so it means from liquid to the gas phase, that actual boiling temperature is 1363 Kelvin. And the Zn is 1180, and then you have standard entropy of vaporization, standard enthalpy of vaporization, okay? It's given. So that means from this one, we can calculate standard Gibbs energy of vaporization. In fact, standard Gibbs energy of vaporization should be 0. Yeah. Okay? Because there's the continuation of Gibbs energy from liquid phase to the gas phase. So if you just sum up together with the delta H minus T delta S, which is delta G of reaction, that should be 0. Okay? So you don't need both of information. So all these three, among these three, if you know the two information, we can get the rest of the remaining one. Yeah? Do you get it? Do you understand what I mean? So delta G of any kind of phase transformation, alpha to beta. So when you have the pure component, so for example, let's assume I have A solid or A liquid or A gas phase. So it's the same element, same component, same species. It's only changing each state from solid to liquid or liquid to the gas phase. Yeah. So when you look at this kind of thing in terms of the graph, temperature and the Gibbs energy of species, pure species, so pure A in this case. So you have, this should be solid, liquid, gas phase. Okay? And this one we call it melting temperature. And this one, vaporization or boiling temperature. Yeah? So at this point and at this point, the Gibbs energy solid and liquid should be same, and Gibbs energy liquid and the gas phase should be same. When you have phase transition, the Gibbs energy should be same. Yeah. So in both cases, delta G of reaction at reaction temperature, that transition temperature. So transition temperature. Should be 0. Yeah. Solid minus liquid or liquid minus gas at that transition temperature should be 0 because same value. Yeah. But if it's not the same, that transition temperature, this is not 0. But however, at that exact transition temperature, it should be 0. Okay. And this is delta H of reaction minus T delta S of reaction. Okay, and this one should be transition temperature. Yeah? So, because this is 0, if I know this one and this one, I know this one. If I know this one and this one, I can get this one. If I know this two, I can get this one. So, you don't need all three information. You need only two information for this kind of, at this kind of specific condition, transition temperature. Okay? But anyway, we have all of them, luckily. And it should be internally consistent, of course. So we have this kind of standard Gibbs energy for phase transformation. And then now, okay, the question is, okay, so Zn and the magnesium liquid phase, liquid solution is ideal solution. Okay, that's good. And then ideal gas is the monoatomic gas phase. So it means gas is only Zn and the magnesium mixture. So there's no Zn2 gas or Zn-Mg gas phase like this. So it's only Zn and the magnesium. Okay? And now we have liquid phase in equilibrium with the gas phase at 1250 degree Kelvin. And the P total is 1 atm. And calculate the composition of liquid phase as well as the gas phase at equilibrium state. So, I mean, when you look at this first time, it looks very strange. Okay, so it doesn't even give what's the composition of solid phase or liquid composition. And it doesn't give any composition of gas phase. It just says that we have the magnesium and the zinc binary system, and then I have equilibrium state. What's the composition of liquid and the gas phase? Based on this thermodynamic information. That's it. Okay? So let's try to draw the schematic diagram and see whether this is enough, this information is enough to solve the problem or not. So this is number 10. So I have liquid phase, gas phase, yeah. So 12 Okay. So let's think about what kind of chemical reaction we can set up here. Of course, I mean, magnesium become magnesium, zinc become zinc, liquid to the gas phase, yeah. So Mg, liquid, become Mg, gas phase. So this is definitely one of equation, and then the other one is then liquid, gas phase. And this delta G not 1 is delta H not 1 minus T delta S not. And this information here, I mean, you have that vaporization information, yeah? So delta G of vaporization, so of the magnesium, is delta H of vaporization minus T delta S of vaporization of magnesium. So we have both information. So we don't care about that transition temperature, but we have delta H, delta S naught. That's these two values. Per mole, yeah, small s, small h, so per mole of magnesium. So we can enter that information here for magnesium part. And then this will be, so H, so this is 127.0. So let's look at this information. This is obviously wrong. This table is wrong. It's not internally consistent. As I mentioned, delta H should be same as delta S times TV, yeah? But if you look at it, it doesn't make sense, yeah? So H and S actually is mixed up. So the first one, so on the table here, so on the table, where is it? This should be delta H. This is delta S. Okay? Then if you make a delta H minus T delta S, then it actually make a consistent actually the result. It becomes 0. Yeah. Swap? What do you mean? It's joule per mole. Oh, is it? So if these two together, it make this one. Okay, then this should be, the unit is wrong here. Thank you. So this unit is wrong. So this means, so this delta HV in this case is 127.40, yeah, good. 127.40 kilojoule per mole. Is okay? So she said, that actually makes sense more, that makes more sense. And this one is for magnesium 93.47 joule per mole Kelvin. Okay? So whenever you have this kind of information, you have to be very careful. It's kilojoule. Okay? So when you are in a hurry, typically you just forget and then you just say, okay, this is same unit, and then you just go ahead and you make complete wrong actual answer. So now this means times 1000 joule, yeah? So that's delta G1. And delta G2, so delta HV in this case is 115,330 minus T times 97.737. Is okay? Okay? So the unit is wrong. So this unit should be here, this unit should be there. Okay? Only swapping the unit. So at the given temperature, 1250 degree Kelvin, we know what's the actually delta G naught 1 and delta G naught 2. Okay. So we have two chemical reaction, and we know the Gibbs energy of this chemical reaction. Now, let's try to actually look at whether this two equation is enough. Two chemical reaction is enough to solve actually the one variable here. So if I know the mole fraction of this one, I know mole fraction of this one. If I know mole fraction of this one, I know mole fraction of this one. Yeah. Just 2 together is 1, 2 together should be 1. So we have 2 variables with 2 equations. So we can solve it actually. Okay? So if I just take the first part, when delta G equal to 0 at equilibrium state, delta G naught equal to minus RT ln P magnesium over activity of magnesium. And this is same as mole fraction of magnesium because this is ideal solution. So activity coefficient equal to 1. Okay? And second one, same way, delta G naught 2 equal to minus RT ln P Zn, and then A Zn. This is mole fraction of Zn. Okay? And we have 2 more. One ATM, total pressure, and XmG plus XZn equal to 1. So if you replace magnesium with zinc for all the equation, then you can solve actually the pressure of the Zn and the mole fraction of Zn in the liquid phase. Is it okay? This one?
No, I mean, then they have same level because that should be total pressure and this should be.
Yeah, these 2 together should be 1 total pressure, yeah?
I mean, if you calculate that
Which one? So this is gas phase, and liquid phase. Yeah. Okay? So it's 2 different bills, yeah. And then of course, I mean the partial pressure is the mole fraction of the gas times total pressure. But total pressure, we say that it's 1 atm, so yeah. So partial pressure is same as the mole fraction of the species in the gas phase. Okay? So we need the second order polynomial equation. Is good? This is very long question. Let's do this one later because it will take really entire this whiteboard, okay? So let's do this one later, okay? I like the question, but it take much longer time. Let's look at this question first. So now chapter 8, regular solution. So, do you recall that the regular solution is Gxs is omega xa xb. Okay, and this is, there's only one term, and that's actually the Gxs can be function of composition and temperature, but especially when Gxs value equal to constant times mole fraction of xa power 1 mole fraction xb power 1, so it's a symmetric term. In that case, we call this one as a regular solution. Do you recall this? Okay. So we want to actually apply this special case. So in the previous question, we talked about Hennian active coefficient, Laurentian active coefficient, yeah, Hennian solution, Laurentian solution, and ideal solution. That's what we have done. And this one is mainly for the regular solution. Okay. Okay, so we have copper and the silver solution again. So we want to remove the copper impurity from the silver, and we are blowing the pure oxygen, 1 atm, and into the AgCu base, and slowly the Cu2O is forming. And the liquid alloy AgCu is regular solution with that regular solution parameter. Okay. And if the reaction is carried out at 1000 degrees Celsius, what is the minimum amount of copper obtained? Okay. Let's go back to the regular solution again. So G of the solution equal to XA GA plus XB GB, and this is basically partial Gibbs energy, and then this partial Gibbs energy call this one as G-access parameter. Yeah. So G-access parameter, some people actually say that instead of G-access parameter, this is G mixing parameter, delta GO mixing parameter. Okay. So when you mix it, some additional energy which is forming delta GO mixing, and because ideal delta GO mixing is this one, entropy term, so this is the excess energy, excess Gibbs energy of mixing, M. Or some people say that all this one is basically same meaning. Okay? And G excess or delta G excess is delta H of excess of mixing minus T delta S of excess of mixing. Okay? So this term is basically same term. Okay? And now, when it is regular solution, G excess should be omega, so some constant term. This is only from this delta H of excess mixing, so M mixing, and minus T delta S of excess mixing. This is 0, and so this is same as this one. So only enthalpy, excess enthalpy of mixing is counted inside of this regular solution parameter. Is it okay? Is it clear? Why this is 0? Because this is constant, and this is a temporary dependence term, simply. That's most obvious way to tell you. Okay? So delta H of mixing is regular symmetric term, and when omega is positive, you have the positive enthalpy of mixing. Okay, excess enthalpy of mixing, or ideal enthalpy of mixing for the regular solution is 0. So in here, this is entropy of mixing. There's no enthalpy of mixing. Ideal solution, there's no enthalpy of mixing. Yeah. Ideal gas phase, we say that there's no enthalpy of mixing. There's only randomness generate. The entropy of mixing generate. The solution become more stable. That's the ideal solution. Okay. We assume that there's no interaction between the species, no energy difference between the species. Okay. But when you go to the regular solution, the regular solution parameter is basically directly related to the relate to the enthalpy of mixing. Okay? Or we can say that it's excess enthalpy of mixing or it's a total enthalpy of mixing because ideal enthalpy of mixing is 0 anyway. Okay? Understand? So, if you know this background, let's look at that question again. So, okay, so we say that it's regular, so blah blah blah, AgCu is the regular solution, and then delta H of mixing, M. Now, I mean, M is on top, I mean, depending on the notation. Sometime in the bottom, sometime in the top, whatever, you know, M or MIX, you know, whatever it is, or solution sometime. So delta H of mixing equal to 13390 XAG XCU. So this means omega term in the regular solution parameter is 13390. That's what it means, joule per mole. Okay? And if the reaction is carried out at 1000 degrees Celsius, what is the minimum amount of the copper could be obtained from here? Okay. So this is almost same question as we did for the Hennian solution. So very first question in the chapter 7 was we give the Hennian solution parameter, Hennian active coefficient parameter, sorry, of the copper and then ask you to find out what's the minimum amount of the copper we can remove under certain condition, yeah. But in this case, we don't have that Hennian solution parameter, but instead of it said it's Hennian solution, it said it is regular solution. Okay. Whether it's regular solution or not, if you want to actually solve the problem, you need the activity coefficient. You need the activity coefficient, not the regular solution parameter. So this regular solution parameter somehow should be changed to the activity coefficient. That's the relationship here. Here. So omega is regular solution parameter. So when this is regular solution and omega is regular solution parameter, then activity and then delta H of mixing or delta H of excess of mixing should be expressed by omega XA, XB, or even G excess of mixing. It's all same basically. It's expressed in this way. Under this condition, RT ln gamma A. So A activity coefficient times RT ln gamma A equal to omega XB square. Okay? Same thing. RT ln gamma B equal to omega XA square. So this is the relationship between the activity coefficient and regular solution parameter. We're going to derive this one later when we actually learn the so-called Gibbs duem equation. But at the moment, let's just assume this is the valid, actually, the formula. So this is valid relationship between the activity coefficient and the regular solution. So this is only apply when your solution is regular solution. Okay? Let's just assume that we have this equation, okay? And then based on this, let's try to solve these two questions here. So, number one, question number one, number two. So we wanna do this one, Cu solid phase, yeah, at 1273. this value is given, 1273 value is given in the question. So we have to solve this one, and to 1273 Kelvin, and this is AG CU. Okay, we want to know what's this quantity in the end here. What's the minimum impurity we can control, assuming that this is regular solution. Okay, so we have solved this one. So at equilibrium, again delta G equal to 0. So delta G naught equal to minus RT ln and activity of Cu2O solid, activity of Cu square PO2. And this is 1 atm, this is gamma Cu X Cu. Okay. So now, when you actually have this kind of problem, so let's just try to, then this is 1, then this is delta G naught equal to minus plus RT ln gamma Cu plus ln X Cu 2 times. Is it correct? So it's a square, and then we just flip, so make it plus, and then we take out that power 2 to the front side. Okay? And because I didn't actually enter the gamma Cu value directly from this relationship, but now we know that so RT ln gamma Cu omega X AG square, yeah? That's the relationship we know from the regular solution. Okay, this is omega X 1 minus okay. So if I enter this relationship here, then this term is more easy to actually express, yeah? So instead of just enter all this number and then solve it and then you back actually to enter this number again, we just take entire RT ln value and change that to the omega X B square. Then you can save a little bit time. And of course, this one you cannot solve because this is not second order polynomial equation. It's much complex, yeah? So you need a better computer. You cannot just solve by hand, yeah? Well, if you are really smart, you can solve it probably. But I cannot solve. Okay? So when you have regular solution, you always end up this kind of actual problem. It's not typically not second order polynomial equation. You have to solve. You need some better calculator. And when you have this kind of problem, in the end, in the term of final, you can try, if you are calculated, most of the calculators solve this one in this day, I think. But if you are not, you can say that my calculator cannot solve the problem, so I just leave the final equation here. That's okay. It's not your fault, it's your actually calculator's problem. So. Okay, let's check the question number 3. So it's a similar question. Okay, now we have the lead, liquid lead, and then we have the copper as impurity. And we are adding PBS into this solution. So, and then the following chemical reaction happen to make a certain amount of Cu2S. So PBS reacting with the Cu and become Cu2S, and then PBS become reduced to the PB. And that's the chemical reaction. And this is the 1823 Kelvin. If both PBS and Cu2S sulfide observe on the surface of liquid PB and Cu, and assume that these two, Cu2S liquid and PBS liquid, stay as a separate phase. So this is one information you have to be very careful. So each solution, Cu2S and the PBS, both of them is solution, but we assume that these stay always separate phase. So it means the activity of Cu2S, activity of PBS equal to 1. Both of them equal to 1 because separate liquid phase. Okay? So it's not solution, not chemical solution, it's a separate phase. Okay? So calculate the amount of the copper in the lead, in the liquid at equilibrium state. And we have this. So delta HCU, now look at this. Delta HCU equal to 42170 mole fraction of XB square. So that's the another one here. So this one, in fact, here, this is partial enthalpy of mixing of A. So this is partial. So it's partial, and this one partial enthalpy of mixing of B. That's actually the information here. Why is that is, so we said that this is enthalpy of mixing, yeah, delta HO mixing. And theoretically this delta HO mixing, or excess or not, this is delta HO mixing. It's the same as this one because total HO mixing is excess plus ideal. Ideal is 0 basically for the regular solution. So this and this term is basically same. And so this is mixing term. And we can separate this one as a partial enthalpy of mixing of A and partial enthalpy of mixing of B. So like a Gibbs energy. Gibbs energy is mole fraction of A, partial Gibbs energy of A, mole fraction of B, partial Gibbs energy of B. So partial enthalpy of, total enthalpy of mixing is delta H of A mixing times mole fraction of A plus delta H of mixing of mole fraction of the B times mole fraction of B. So by definition, this is working. Okay? And this is omega XA, XB, yeah? From the regular solution. Okay? Then, and then, even though you don't know the, now let's assume I know the answer, and then the answer is, this one is omega XB square, and this one omega XA square. Then if you enter it, omega XB square times XA, omega XA square times XB, then XA, XB is the common term, and then you'll get eventually this term as it is. Okay? I mean, because we know the answer, we can get the answer here. But later, when we actually do the Gibbs-DM relationship, we actually take this one and we derive this one later. Okay? But at the moment, just accept it. And this is the answer for this one. Okay? So it's a partial. So this is this term, then this term. So if you look at actually inside of this term here, RT ln this one is G excess parameter, yeah? So this one should be same as this one too, yeah? And then especially, so now RT ln gamma A mole fraction of XA, RT ln gamma B mole fraction of XB. So RT ln gamma A be delta H of A, yeah? And RT ln gamma B should be delta H of B mixing. And then that actually should be omega XB square and omega XA square too. So all this one is internally connected in this way. Okay? Bit tired there. I know you have to remember this one. Or you don't have to remember because it's open book. But at least you have to know that there's a relationship. There's a relationship between regular solution parameter and the partial enthalpy and also activity coefficient. Okay? But in reality, when you graduate, how many times are you going to use this one? 0. You're going to always use the Hellion active coefficient. Ideal active coefficient, ideal solution active coefficient. But almost no chance to use the regular solution parameter. But this is, we are doing education, very simple. We are using very simple case, and regular solution is one of that simple case we can test for the solution. So, student, it's just for the, I would say it's really just for the testing the student or teaching you, It's not really very useful. Anyway, from my point of view, not very useful, but some people believe this, but okay, good. So now if you understand this one, let's go back. Okay, so that delta H of partial enthalpy of mixing is given by constant times mole fraction over the other component. That means that information is already tell you this is regular solution. Okay, so this information here, even though I didn't say it's a regular solution, this information tell you that this is regular solution. And then this 42170, 42,170, this is regular solution parameter. You have to keep this one. Okay, you have to get this idea. Okay, so if I know this one, I can calculate now activity coefficient, because I know the activity coefficient basically. Then you can just enter all those things and then try to calculate, then you can get it. So for example, this. So number 3. The chemical reaction is so simple. So this is PBS liquid plus Cu equal to PB liquid plus CuS or Cu2S to Cu2S liquid. And I know this delta G naught of reaction. Then at equilibrium state, and this is 1 because it exists as a separate liquid phase. So pure liquid Cu2S and pure PBS liquid phase. So activity equal to 1. And this one is now active coefficient times mole fraction. And same thing, this is active coefficient mole fraction. And this one and this one can be calculated by the regular solution parameter. So okay, so you can change everything into the mole fraction of kappa and then have the one equation with one variable and you can solve it. Okay, but this one is of course 1 minus Cu. Yeah. Okay, it's a little bit complex equation, but it's complex. The equation to solve, but you can solve it mathematically. Theoretically, it's possible. Good? I think that's, yeah, so let's look at the other one. Now we have the iron manganese alloys, And in the furnace, we actually put this liquid iron manganese furnace, the alloys into the furnace. And liquid oxide, FeO, MnO, is forming on top of this actually liquid metal. And this two solution is in equilibrium with the gas phase, in which the partial pressure of O2 is 7.0, 10 to the minus 11 atm. Assuming that the two liquid solutions, so metallic solution and oxide solution, is both of them is ideal solution, and calculate the mole fraction of the iron in the metallic phase and mole fraction of FeO in the oxide phase, and oxide phase we call it slag. This is not very complex. This is question number 6. So we have, so this furnace is 1873 Kelvin. We have basically three phase here. Okay. So here is iron, manganese liquid phase. Liquid phase and O2. This is ideal solution, and this is gas phase. So ideal oxide solution. So this kind of oxide solution, we call this one as a glass melt, liquid glass, or in the metallurgy, typically we call it as a slag. In geology, we call this one as magma. It's the same, or oxide, liquid phase. Okay, so this one, so basically we know the PO2 here, yeah. So when you have, so when I should first learn the thermodynamics, I was very confusing. Okay, so when you have three layer kind of structure like this, is this one is also equivalent with this one or not? I mean, this one I see, okay, this is in equilibrium, yeah. It's in equilibrium state together. At the interface, you should have equilibrium in the final state. And these two, you should have equilibrium in the final state. And virtually, these two is also in equilibrium. Because inside of system, everything is equilibrium state. So whatever chemical reaction you make inside of system, it's all in equilibrium state. Okay? So you can set up whatever chemical reaction you like by using the component inside of system and using the condition inside of system. Okay? So even though like you even have like some solid phase here, so let's just some even solid phase here, this solid and this gas phase is also in equilibrium. It's just through this one, through this one, through this one, and eventually this is in equilibrium state too. Okay? So when you say your system is in equilibrium state, you can assume that any component inside the system can be combined together and make chemical reaction, and that chemical reaction should be in equilibrium state. Okay? So this is the 10 to the minus 11, so P. So, and then we have this iron. We know this delta G naught of reaction 1. These two. And we want to know mole fraction of this one, mole fraction of this one, yeah? And luckily we know the partial pressure of oxygen. So we know the partial pressure of oxygen. That's the one I think. So we need at least two equations, two independent equations, yeah? To know the two independent variables. So if I just write first one, so if I just take very first one at equilibrium state, so delta G naught 1 equal to minus RT ln activity of FeO and activity of Fe and PO2. So I know this one, so it's 7.0 10 to the minus 11 atm, and this is mole fraction of iron, this is mole fraction of FeO, because it's an ideal solution. Activity coefficient is 1. So activity is same as It's mole fraction, yeah? So there's two variable with one equation. Okay? And you can take also number 2 if you like. And then you can get delta G naught 2 equal to minus this is 1 minus XFE so you have two equations with the two variables. Yeah, so it's not very complex. Or you can combine it together. So one independent equation and then one combination equation. That also give you the another set of actually the another two set of equation which is independent basically. Yep. That's wrong. 1600 degrees Celsius. So you can just assume that the K is the 1600 degrees Celsius. Delta G not 1600 Kelvin. That's Celsius. Sorry about it. There's so many typo. It's been there for 10 years. I haven't changed it yet. I'm not diligent enough. Because if it is 600 degree Kelvin, iron and manganese is not liquid solution. It's a solid. Okay? Good? I think it is too late to go back to actually that 12. Because the question number 12 at least take 10-15 minutes easily. So if I start now, we're actually going to finish it in the 2 o'clock. So I don't want to hurry up. Any question? Okay? So activity, now you know the activity. So there's much more thing you can actually solve. Okay? And now you know the activity and regular solution. So next week, what we are going to learn is, we just solve this final equation. And then we're going to learn a little bit more about the partial thermodynamic property. So we will talk about partial Gibbs energy, partial enthalpy, but now we're going to look at more than actually these two. So partial molar volume and etc. And then eventually we'll derive this so-called Gibbs dm equation. No question? Good? Okay, see you next week.